All right, guys. Can you guys hear me? Oh, good. You guys hear me, right? Okay. So let's give it one more minute. Okay. Because today is the first lecture. We always have some technical issues for the first lecture. Some students will always wait for the last minute before they realize they can't even log into the system. All right. Just give me one more minute. We still have some students that are struggling, try to log in our classroom. I'm pretty sure for this classroom, there's no waiting room. There's no password. Is that right? So when you guys log into the system, there's no waiting room. You do just directly go to the classroom. Is that right? That's good. Yeah, because these days the Zoom keep changing their security settings. Because I also get some feedback saying that even for the regular classrooms, they will create a waiting room before you can really successfully log into the system. So we're trying to make sure everyone is working properly. Okay, one more minute before we get started. Okay. Yeah, I try to disable the waiting room exactly, but sometimes and they just they just enforce the waiting room as a security enhancement. Because in this classroom, right, there's no password because I create this Hawk or Thor class for a long time. However, when I create the mathematical thought lecture, that when I create that URL, I have no option but choose to set up a password. I can't even disable the password setting because that one has been chosen by default. Because these days, so many complaints that are against the Zoom application, so they're trying to pretty much hardening these security applications. Okay, so I think we can pretty much get started. Okay, guys, so let's get started. Hey, guys, welcome to my North American math competition lectures. I think pretty much most of the students were the old mates. So instead of spending a lot of time doing a cliche, I'm just gonna make it a little bit straightforward, but we still have some new students. I wanna give you guys a very quick overview about our lecture, how it works, what is the organization, so on and so forth. All right? So I think just like 5 minutes maximum should be good enough. So basically, this is a lecture aiming for the concepts, right? Instead of having the boot camp, these days we're more focused on a specific topic. In each topic, I'm already give you guys a forecast, right? What we will be covering for the next few lectures. In today's session, we're going to use 10 lectures talking about the sequence. So before we get started, I want to give you guys a very short and brief introduction talking about how the organization works. This is like an online lecture, right? Normally you should have the face-to-face lecture, but these days due to the coronavirus, I don't think there's any face-to-face lecture happening, right? So this is like an online lecture, but I do understand, but I do believe that even though this is an online lecture, the interaction is always more important, right? Even though you're sitting in front of your teacher, if you never talk, so no one will be able to read your mind. So try to, if you have any questions, you can basically let me know. There are two ways for you to participate in this interaction process. The first one is you can use a chat function. If you are familiar with Zoom, in your control console, there should be a mute, stop video, so on and so forth. In the last option, you'll be able to see three dots saying more, right? If you click that three dots, there will be a drop-down menu. So that drop-down menu the first one will be chat, right? You click the chat, you'll be able to go to the chat board. There are two ways for you to shout it out. You can either talk to me or talk to everyone. That being said, everyone can see your questions or see your answers. Or alternatively, you can privately talk to me. As long as I raise a question, you can privately let me know. As long as you see your answer is correct, I might be asking you to, basically let everyone know how your answer works. So like one chat option. The other option I think is more, I think I'm actually more prefer is using your audio, right? You all have a microphone. So instead of typing, right, it is better just to unmute yourself, basically, shout out your answer, right? In the entire process, if you have any questions, you can just let me know. If you think I'm talking something doesn't make sense, also let me know, right? This interaction process is always more than valuable in the teaching and learning process. Okay. Second one is the homework. For each lecture, I'm going to be give you a homework. Normally speaking, 3 problems. So you have 1 week to finish the problem. And as long as, let's say, our lecture focuses on Saturday, right? So the deadline is actually yesterday. Oh, excuse me, is actually like 1 day before Friday. Friday will be considered as the deadline for the next lecture. So normally you have like a week to finish your homework. As long as you submit your homework on time, I will be mark it for you. And if I think your homework is correct, I might be asking you to give us a quick explanation. So normally this is how it works. Every lecture, I'm going to give you 3 homework, 3 problems as a homework. At the very beginning of the next lecture, I'm going to be reviewing these 3 problems. I'm going to be asking some students to give us the right answer, and I'm going to give some complement and official answers if there's any, on top of your solution. Just try to make everyone you can participate in this process, right? And the last one is that for each lecture, not from today, pretty much from the next lecture, I'm going to be asking one student to give us a quick presentation, 5 minutes maximum. Don't go for too long. A quick presentation. You can pick up whatever questions you like, as long as they're relevant to the topics we're talking about. They're more than welcome. You can pick up questions from the AMC, from the different kinds of math competitions, or even your homework. The most important thing is I want you guys, when you're doing the presentation, instead of reading the answers to us, try to give us the reasoning, why you choose this problem, and what do you think when you are trying to solve this problem. Because the $1,000,000 question I will be asking you guys for the entire course of the lecture is, how do you think? Instead of giving the problems one after another, there's millions of problems there. You can't even cover half of them, right? But the strategies, the mathematical thoughts behind the problem are the focus of our entire lecture. This is the way I'll be showing you guys in my lecture, and hopefully you guys, when you're doing the presentation, you'll be able to learn from me. Also try to explain the reasoning after each problem. Okay, I think just pretty much a short and brief introduction because most of the students are old mates, so I don't want to spend too much time talking about this. And any questions? So far, so good. In terms of the camera, I wish you guys can turn on your camera. Like the reason behind that is sometimes people are a little bit shy. If you don't understand what I'm talking about, people sometimes, they don't even talk, but I can read from your face. So if you see some students, you got like, their eyeballs, something like this, I might to basically repeat, right? But this is not a compulsory. If you don't think you want to turn on your camera, you have your human rights, right? So it's up to you guys. But I think based on my experience, is actually give you guys more advantages if you can, I can see your face, I can figure out, if you understand me or not. Right? A little bit cliche, and I think we can get started. Okay. So like I said, in the next 10 lectures, we're going to talk about the sequence. So let's start a new page. We're going to talk about the sequence and its properties. Okay, first of all, you guys, if you're familiar with different kinds of math competition, you know that there are 4 major directions for the math competition: geometry, counting and probabilities, number theory, and algebra, right? And we both know that the number theory is a very complicated part. You always see the number theory problem in the last 2 or 3 problems. And also, I want to say that because algebra is pretty broad section, right? It contains different topics, functions, trigonometries, sequence, so on and so forth. And we have to say, if we have to pick up a problem, the last problem from the algebra territory, most of the time they will pick up sequence. So sequence, we'll say, is the most complicated part for the algebra section because it is easy to be combined with the polynomial problems or the counting problems or the number theory problems. So that being said, for the counting section will be a relatively difficult section. Talking about the algebra, it should be a lot more difficult compared with function or some trigonometries, so on and so forth. All right. So talking about the sequence, we should be very familiar with the definition of the sequence, right? A sequence means what? Let's say we use AN, a curly bracket, to denote a sequence, right? So the sequence just basically means numbers in a certain order, right? That's the definition for sequence. Well, this certain order can be something very strong or can be something very loose. For instance, a strong condition means, let's say we're familiar with the arithmetic sequence or the geometric sequence, right? Those sequence, every single term, they are so strict. You must basically follow all the patterns to make sure it forms the arithmetic sequence. So this is like a very strong pattern. Or you can also have something very loose. Let's say I want to have an increasing sequence, right? Or a decreasing sequence, right? This is also a sequence. There are numbers formed in a certain order. Increasing, you can find whatever numbers as long as they follows the increasing fashion. It's good to go. Or we can just have like no patterns. No pattern will be also considered as a pattern, right? This pattern name is no pattern. For instance, the random number. The random number can also form a sequence, right? They're just basically no patterns. All right. Or you can even have like the same element. We call it the constant sequence, right? Or the constant number, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, can also be considered as a sequence. So the definition really speaks for itself. As long as the numbers they are formed according to a specific order or a specific fashion, these numbers will be considered as a sequence. For the fashion per se, we're not so strict. You can just do whatever you like. All right. So before we jump to the real part of sequence, I think you guys should be familiar with set, right? As a high-level lecture, you should be familiar with a set. So here I want to give you guys a very quick comparison between set and sequence, because normally set, we also use the curly bracket to denote a set, right? Also curly bracket. And also curly bracket to denote a sequence. So from time to time, how can we differentiate between these two concepts to make sure there's no confusion between the two, right? I believe there are two major differences between a set and also a sequence. The first one is order, right? Order. So like we said, sequence is numbers in a certain order. So for sure, order matters. Let's say 1, 2, 3, 3, and 3, 2, 1. For sure, these are two totally different sequences because they follow the different order. While if you're familiar with the set, actually, in the set's definition, order does not matter, right? So 1, 2, 3 set is exactly the same as 3, 2, 1 or 2, 3, 1, like whatever. All the numbers in the set, the order doesn't matter. So this is the number one difference between a set and a sequence. The second part is we're talking about duplicate elements. We still start with the sequence. In a sequence, duplicate elements is totally acceptable, right? Even though I can have the constant sequence, a sequence has nothing but 1, 1, 1, 1, 1, 1, 1, 1, right? Or like a binary sequence, 1, 0, 0, 1, 1, 0, whatever, whatever, right? You can only have two items, 0 and 1, but you can just basically do whatever fashion you like. However, from the concept of set, duplicate numbers, duplicates, they're totally prohibited. Is that right? In the set, you can't have 1, 1, 2. This is not a set. This is actually against the definition of set. And now to say what is the reasoning, this is against the definition of set. So that being said, order and tolerable to have a duplicate elements or not, these are the two major differences between sequence and set. All right. So moving forward, I like to give you guys a little bit preview what we are going to talk about in our 10 lectures. At the very beginning, we're basically going to give you guys some basic concepts, basic principles. So these are considered to be the prerequisite before we move on to the real territory of the sequence. So two things. One is we're going to introduce the mathematical induction method. This is one of the topic for today's lecture. We're going to introduce a very important method, how to prove some sequence-related problems. Maybe you're going to say later, this is not only for sequence. As long as you're dealing with some positive integer-related problems, mathematical induction method can be considered a very powerful tool to help you out. This is for number one thing. Second part, we're going to introduce you the minimum principle and proof by infinity descent. So this part might not be very familiar for most of the students, but this is actually a very important concept when we're talking about the proof by contradiction. We always know that sometimes whenever you see certain types of problem, you like to go for the proof by contradiction. However, the million-dollar question is that how can you find out the contradiction, right? We both know that proof by contradiction only have two steps. Step one, let's say something you want me to prove does not exist or does not valid, right? You want to construct something opposite. That part is easy. Or the second part is based on your hypothesis, based on your suppose, you're going to find out what is the contradiction, right? So the million-dollar question is how can you find out the contradiction? Sometimes people had a hard time finding out what are the contradictions. So minimum principle and proof by infinite descent actually give us a very good direction. Sometimes the contradiction can be found in this kind of direction, especially a lot of weird problems. Later, we're going to show you how this weird problem works. Right? As long as we have the basic principles, like the prerequisite, we'll be able to talk about something like the general formula and the recurrence formula, right, of a sequence. Right? The sequence have the very two important way to do the denotation, either the general formula or the recurrence formula. I'm going to give you guys a little bit of idea how to basically, define or determine a sequence general formula or a recurrence formula. Or from a recurrence formula, how can I find out the general formula? Basically, the relationship between these two formulas, right? For instance, I'd like to give a very simple example. For the arithmetic sequence, we know that this is the general formula, right? This is the general formula for arithmetic sequence. And this is the recurrence formula. Let's say an minus 1 equals to d, right? How can you find out the relationship between these two types of formulas and maybe using one to determine the other? So this is actually a very important topic. You actually see them a lot in the AMC problems, right? So moving forward, we're going to introduce the very famous twin brothers, the arithmetic sequence and geometric sequence, right? Most of the problems are actually based on these two sequences. Not necessarily they're completely testing these two sequences, but some problems are actually elaborated based on these two sequences. Also, we're going to introduce a very important topic, which is the high order arithmetic sequence. This part you might not see very often in different kinds of math competitions. In different kinds of math competition lectures, but this is actually something very important. A lot of the high techie problems that are derived from the high order arithmetic sequence. And here we're going to introduce the differential method. This is also an important method how to determine some high order sequence, some of the weird formed sequence. What is the starting point? All right. Moving forward, we're also going to introduce the periodic sequence. As you guys can recall, a lot of AMC problem and some like Euclid problem as well, the sequence per se have some period, right? Periodic sequence is also a very important topic in the math competition. So we like to introduce some unique properties for those types of sequences. And we're also going to introduce the Fibonacci sequence. Fibonacci, right? Fibonacci sequence. Fibonacci sequence, I think most of the students, you are aware of this, you heard about it, and you know basically, right? Any term is actually the sum of the previous two terms. So a lot of interesting problems are actually based for the on the Fibonacci sequence. So we like to give you guys some ideas how to use this Fibonacci sequence. And on top of that, we also want to introduce some how to find the general formula. Finding out the general formula of a sequence can be very challenging from time to time. We're going to introduce some eigenvalue solution, or some fixed point solution. Different types of Flory solutions try to determine the general formula of a given sequence. So I think this is like a short and brief introduction talking about all those, the important topics we will be working on in the next 10 lectures. All right, I think you should have no problem talking about this, right? So any questions? So far, so good? All right, so let's go to our first topic, the mathematical induction method. Mathematical induction method. So we have a subline, a tool for integer related proof. Before we get started, let me do a very quick survey. Are you all familiar with the mathematical induction method? Can you privately let me know if you feel a little bit shy? I wish everyone let me know because we need to know where we are. Okay? Please, everyone, don't feel shy if you are not so familiar. Okay? It's not a big deal. Can everyone give me a feedback? Okay, then that's good. So it looks like pretty much everyone is familiar with mathematical induction method, so we can move a little bit faster. We'll focus more on some real problems, okay? So like a little bit overview about this. Proof is actually, what should I say? This is like a way how to do the integer related proof. I have to say like proof is actually something very complicated for the mathematics. So we can say a proof is actually occurs in mathematics for all the eternities. We keep saying that, for the mathematician, calculation is easy, calculation is cheap. Well, proof is something very complicated. So this is more like a curse for most of the mathematicians. So in the entire mathematics territory, there are basically two types of proof. One is the geometry proof. The other one is the algebra proof. Okay? So at this moment, there are not so many world-class geometry problems left to be proved. Most of the geometry problem has already been proved. We're talking about the world-class geometry problems because we basically have the coordinate geometry, right? If you guys are familiar with the coordinate geometry, any kind of the weird geometry problem, as long as you have the xy, right? Xy coordinate, everything can be algebraized, right? A complicated geometry problem, as long as I put it into the xy plane, I basically let you to do all the coordinates, everything can be proved by using computer. It's fairly straightforward. So that being said, in the last 2,000 years, a lot of geometry-lists find so many difficult problems, but most of them has been proved. There are not so many world-class geometry problems left to be proved. But of course, there are still some. I'll basically give you guys two examples. I think you guys should basically heard about it. One is the famous the square ring the circle. Squaring the circle. If I have a circle, how can I create a square to make sure the square has exactly the same area of the circle? So this is impossible at this moment to use it to basically solve this problem or prove this problem simply by using your ruler or your compass. We're talking about only the ruler and compass. For now, it is impossible for us to solve. This is like a world-class problem remaining to be solved. The other one is actually also important, is the angle trisection. How can I cut an angle into 3 different parts, right? Three equivalent sections. To have a bisection is so easy, everyone knows that. But how can I have the trisection? This is also a world-class problem. Even for today, no one knows how to prove it using simply ruler and compass. But generally speaking, this should be something we don't have too many remaining, okay? However, the algebra proof, there are so many world-class algebra problems, or we can say the algebra conjectures remaining to be proved. Okay, so as a very good example is pretty much all the number theory related problems, right? These are also under the algebra big umbrella. So, as one of the very famous is the famous Goldbach, right? Goldbach's conjecture. I think we should be familiar with from our kindergarten, right? The Goldbach's conjecture. Goldbach's conjecture said every big even numbers can be written as the sum of 2 prime numbers. This big, let's say, a big even number must be able to be written as the sum of 2 prime numbers. This big means as long as more than 4, not necessarily super big. So this problem you see already there for a long time, and no one doesn't really know how to prove it. All right. And in this entire algebra related proof, there actually are one type of them also called, what should I say, track a lot of attentions for the last several centuries. So these are all the integer related proof. All the integer related proof. It means that you're trying to to prove a condition hold for all the integers, not only for one integer, but for all the integers. For instance, I'll give an example, our very familiar 1 plus 3 plus 4 all the way plus n equals to n plus 1 divided by 2, right? So this is actually a type of proof. You're going to touch all the integers, so on and so forth. So this kind of integer-related proof, we actually have a very generic method. This is actually our topic for today's lecture, the mathematical induction method. The mathematical induction method actually contains two forms. I think 99% of the students, you are familiar with the first one. So these are called the first type of mathematical induction method. So let's get started with the first type. And then later, I'm going to give you a little bit about the second type. Okay. The first, I think you guys are pretty much familiar, so I'm not going to spend too much time. But generally speaking, in order to do this, we can say, okay, the mathematical induction method, the quick introduction is, let's say, this is kind of like a review for you guys. Pn is a property about integers, right? If when n equals to 1, Pn holds, right? Second, if Pn holds for one number k, then you can prove Pn holds for k plus 1. Okay? Then you can claim Pn holds for all the natural numbers. All right? I think this is like the basic mathematical conduction method you guys should be familiar with, right? So we have a property, Pn. At the very beginning, if you want to do the mathematical induction method, you are basically doing 2 steps, right? Step 1, try to find whenever n equals to 1, this condition holds. But here, whenever n equals to 1, not necessarily means n must be equal to 1. N can be equal to 2. N can be equal to 3, but n can be equal to a relatively smaller number, right? As long as you find 1, we call it the base case. You can choose 1, you can choose 2, 3, 5, it's not a big deal. You can choose the condition which is the smallest number to make sure this property holds, right? Second part, if you can somehow suppose or hypothesize Pn holds for number k, and based on this condition, you can prove Pn holds for k plus 1, then you will be able to claim that, okay, Pn holds for all the positive integers or like integers, so on and so forth. This one reads very easy, but this actually has a very, very important thing for you guys to know is this part. You want to make a hypothesis, Pn holds for k, and using this hypothesis to prove Pn also holds for k plus 1, then you get what you need. So the most important part is that you must try to do your k plus 1 proof using the hypothesis you did for k. If you're totally doing nothing, you're not really using k, unfortunately, your proof doesn't make sense. You guys follow me? This is the very important part. Always, for the mathematical induction method, you have 2 steps, right? Step number 1, let's say n equals to 1, Pn holds. Step number 2, this is 1. Suppose n equals to k, Pn holds, right? We are trying to prove n equals to k plus 1, Pn holds, right? So that being said, Pn holds for all the integers or positive integers, so on and so forth. It's actually based on different conditions. Well, the $1 million question, like I keep saying, is this part. Whenever you are proving n equals to k plus 1, you must use the condition or the hypothesis you did for n equals to k. If you do some magic, whatever, you prove this without using this condition, unfortunately, your proof doesn't make sense. This will not be considered as a valid proof using the mathematical induction method. Right? Are you guys follow me? This is a very important part. I know some students, they know how to use the mathematical induction method, but they forgot to use the condition from here. This will not be considered as a valid proof. Right? So I'll give a very direct, very understandable example to help you guys do a quick refresh, okay? Let's say you want to say such a statement, Alex is always late for his class, okay? We know this is not a, this is for sure like a false statement, right? But let's say this is like a correct statement. We like to prove this. Alex is always late for his lecture, for his class. What are you going to do? 2 steps, right? Step 1, you find any day, n equals to 1 or n equals to 2 is not a big deal whatsoever. You find out any day you caught Alex late for his lecture, right? Alex is late. And then step number 2, we can hypothesize or suppose Alex is late for the case day, right? As long as I do such a suppose, like a hypothesize, I can use this condition. Okay, as long as Alex is late for the case day, I can prove Alex is late for the k+1 state. Okay, so think about it. This is like an internal iteration there, right? So let's say Alex, the first day, Alex is late. This is actually given by my original base case, right? And then suppose Alex is late for the k state. I have already proved Alex will be late for the k+1 state. Okay, let's say k equals to 1. As long as Alex is late for the first day, he will be late for the second day. You already know that Alex is late for the first day. Then for sure, Alex is late for the second day. Is that right? And then you let k equals to 2. As long as Alex is late for the second day, he will be late for the third day. We already got Alex is late for the second day. So Alex is late for the third day. You see, this is like an internal cycle, right? This is the internal iteration. You don't really have to validate all the terms. It will be automatically validated, right? K can be 3, K can be whatever, K can be n. So that being said, Alex is late for the nth day, right? I'm trying to give you guys a little bit of reasoning why we're doing this mathematical induction method. Do not only remember, that one doesn't make sense. You need to understand why, if I hypothesize K works for this property, and I can prove K+1 also works, then voila, everything works fine. Everything will be worked because you have an internal cycling there. They can basically traverse all the positive integers or all the integers to make sure this condition is met. Okay, so far so good. This is you'll be considered as a review. I think you guys already know this, but I want you guys to know two important things. One important thing is you need to find a corner, or you need to find a base case, right? Base case. Let's come to here. Important thing one, you need to find a base. N equals to 1, 2, 3, 4. It doesn't matter. You just pick up one you like. Most of the time, we choose 1 or 0, some relatively smaller numbers. Second, step number 2, always suppose the condition holds for n equals to k, and using this hypothesis to prove the condition also works for n equals to k+1. This is extremely, extremely important. As long as you can build up such a relationship, this one will turn on like a domino effect, right? The first one works for the second one, third one, fourth one, so on and so forth. You'll be able to prove pretty much everything under the entire positive integer, or so on and so forth. Okay, so far so good? If so far so good, let's go for an easy problem as our quick start. This is like a warm-up. Let's try to prove for any natural number n, 1 square, 2 square, 3 square, all the way n square equals to n plus 1, 2n plus 1. Okay, I think this is a very common conclusion, right? The natural number, the perfect square sum, should be equal to 1 over 6 n plus 1, 2n plus 1. This is actually one thing you need to remember for any kind of math competition, right? Even though you do not necessarily know the proof, but you need to know this conclusion. All right, so let's just try to use, this is an easy problem, just like a warm-up. Let's just try to use our two steps to figure out how we're going to solve this problem. Okay, so step number 1, like I said, n equals to 1. You can choose 2, 3, it's not a big deal, but let's get started from 1. So the left-hand side will be equal to 1. The right-hand side, you just basically plug in 1, right? Also equals to 1. So this property holds. Step number 1 is so easy, right? Step number 2, if, or we say suppose, n equals to k, the property holds. That being said means what? 1 square, 2 square, all the way k square equals to 1 over 6 k, k plus 1, 2k plus 1, right? And then I need to check 2 plus 1 all the way k plus 1 plus k plus 1 perfect square, right? You basically check the other one. Like I keep saying, the million dollar question is, whenever I prove this, I must use the hypothesis I did for the last n equals to k scenario, which is extremely important. So that part, I think, for this problem is easy. I have it exactly here without any problems. I'm just going to plug it in. Okay. K plus 1, 2k plus 1, k plus 1 square. So far, so good? Okay. So moving forward, I just basically do some factorization or some rearrangement. It shouldn't be a huge complicated thing whatsoever, right? It's going to be 1 over 6 k, k plus 1. So you see, I have both k plus 1. Oops. I have a k plus 1 here, k plus 1 here. Very intuitively, I like to do some extraction, factorization, right? This is very understandable. So k plus 1, extract them out, will be k, 2k plus 1, 6, k plus 1, right? So 1 over 6, k plus 1, and 2k squared plus 7k plus 6. Do some quick rearrangement. 1 over 6, k plus 1, 2k plus 3, k plus 2. Right? This is quite understandable, right? And our goal is doing what? Our goal is trying to prove whenever n is equal to k plus 1, I must have 1 over 6, k plus 1, k plus 2, 2k plus 3. Is that right? Let's check it out. This is exactly what I'm trying to prove here. Oops. This is exactly what I'm trying to prove this. So this one can be written as k plus 1, k plus 1 plus 1, 2 k plus 1, plus 1. Is that right? This is exactly when n equals to k plus 1 case. So QED. I basically solved this problem. This is a very easy problem. So I think everyone knows that, right? But the most important thing, like I said, 2 steps. Find out the base case. Second step, try to use the condition that you hypothesized for n equals to k to prove n equals to k plus 1. If you just basically get rid of it, just figure out the magic to figure out n equals to k plus 1, this is not a correct proof from the mathematical inductions perspective, because you didn't create this internal, what should I say, this iteration between k plus 1, so you won't be able to cover all the scenarios. So far, so good? Perfect. So let's go to another problem. This problem is also easy, but I want you guys to find out what the problem is. I want you guys to use this problem to harden your understanding to the mathematical induction method. So this is question number 2. Use the mathematical induction method to prove for any n belongs to this means what? The positive integers, right? N and then have like a star. It means the natural numbers or the positive integers. Okay, you have this. This is also an easy problem. So what is the name of this type of sequence? Who knows? What is the name of this type of sequence? They're just basically 1, 2, 2, 3, 3, 4, blah, blah, blah. What is the name of this type of sequence? You guys know the name? Yeah, it's a telescope, right? It's a telescope sequence. So that's the name of the sequence. So the telescope sequence, you can basically find out what is the n-term sum, right? Okay, so one student gives such a proof. Student proof. He said this. Basically 2 steps, right? Step number 1, n equals to 1, left equals to 1/2. Right equals to also 1/2. I think you just plug in the value, nothing really special. So the property holds. Step 2, let's say n equals to k. The property holds, right? So let's consider n equals to k plus 1. So n equals to k plus 1, the left-hand side will what? 1 times 2, 2 times 3, so on and so forth. So 1 times 2 will be written as 1 minus 1/2, right? 1/2 times 3. Is that right? The last one, I think the last one is n times n plus 1. This part will be written as this, right? And then he find out, you see, all of this can be cancelled. So this will be 1. This is, I think, excuse me, give me 1 sec. This is only to n, right? This is only to n, but I have to write for the one more term, n plus 1, because I'm talking about n plus 1. So another term can be cancelled. 1 minus k, I think this is k. 1 minus 1/k plus 2. So that's exactly what I have on the right-hand side. So therefore, QED. Is it right? I just basically follow step 1 and step 2. So who can tell me, is this correct or not? If the question asks you to prove this using the mathematical induction method, who can tell me if this proof is correct or not? So let me ask some students. Your participation is very important. Let me ask David first.
Wait, hold up. Do you want to like speak?
Yeah, of course. I think it's easier, right? Rather than typing, right?
Well, I don't think that like it's like proves with using like the mathematical induction method, because like he didn't like use like the n is equal to k, the property holds like into like the n is equal to k plus 1. So like he just kind of like did like his own thing, and like that's not how you use induction.
Is that right? You guys follow? So you guys all agree with David? Okay, first of all, I think this proof per se is correct, right? But the entire process, they're like the proof, every single step, it is a reasoning step, right? There's no jump, there's no nothing. The proof per se is correct. However, this is not a correct proof using the mathematical induction. Just like David mentioned. From here, you are actually using the basic property of the fraction numbers, right? And then break them into 2 parts and then cancel them out. This is perfect, but you never use your hypothesis from here. Whenever n equals to k, the property holds, you never use your induction conclusion or your induction hypothesis to prove this problem. So this problem per se is not a correct mathematical induction proof. So this part you guys need to follow me. I think Chris has the right answer as well. You need to use, this is what I keep focusing, right? This I keep emphasizing previously. You always need to use the conclusion, or what should I say? It's like the hypothesis, not conclusion. You always need to use the hypothesis you did for n equals to k to prove n equals to k plus 1. If you forget about n equals to k hypothesis, you just basically do the magic by your own. This will be considered a wrong proof. Okay? So what is the right proof for this? I think the first part is correct. We can retain it. The second part all the way to here also correct, right? But we need to change from here. Whenever n equals to k plus 1, at this moment, I'm going to say the correct proof. When n equals to k, the property holds, okay? Okay, when n equals to k plus 1. Whenever n equals to k plus 1, you're still going to use this 1 times 2, n times n plus a k, k times k plus 1. K plus 1 times k plus 2, right? This part, you basically use your hypothesis. Your hypothesis is 1 over k plus 1, and then subtract by using 1. 1 minus 1 over k plus 1. This is your hypothesis. Then using k plus 1, k plus 2. At this moment, you are free to break this part into k plus 1 minus k plus 2. They're both in the denominator, right? At this moment, you're okay to break it, and you can cancel these two terms, 1 minus k plus 2. For now, this is a correct proof. All right? So try to understand. This is like, I'm trying to give you a real example to prove or to try to denote. Whenever you're using this mathematical induction method, always try to make sure you are really using your hypothesis. Okay? If all good, let's go to some real problems. Some real problems that you need to think about it. Okay? So question number 3. Let's say there is a 2n times 2n square grid. Please prove. You see that we just directly come to proof. Please prove if 1 square has been removed from this grid, the remaining part can be fully covered by using such a L-shape patterns, or like we say the blocks, without any overlap. I'll let you guys finish the writing first. So let's see the problem. Let's say there's a 2n times 2n squared grid. It's kind of like a chessboard, right? It's a grid. Please prove if 1 square, you have 2n times 2n, right? If I just remove 1 square from this total grid, the remaining part can be fully covered by using such a, 1, 2, 3. This is like 3 little thing, create an L shape. This kind of, all the remaining parts can be fully covered by using all this kind of like L-shaped blocks without any overlap. You might use 1, you might use 100, it doesn't matter, but you have to make sure there's no overlap and everything needs to be covered. You see, a problem like this, to be honest, if you do not use the mathematical induction method, this is almost impossible for you to prove, right? You can't really cover all the shapes, right? So think about it. How are we going to solve this problem using the mathematical induction method? This is actually a very good example using the mathematical induction method to prove something pretty much looks like impossible to be solved. So as long as you see such a problem, don't be scared. We always get started according to our two-step criteria. Mathematical induction method says what? Two-step. Step 1, you figure out a corner case. Step 2, I'll figure out like a base case, right? Step 2, suppose the property holds for n equals to k. Prove that it also holds for n equals to k plus 1. Right? So let's get started. I don't even know what to do, but I can basically get started. Close my eyes, basically follow the direction. Step 1, let's do a core base case. When n equals to 1. So you're looking for a 2 times 2 grid. 2 times 2 grid. If you remove one block, one little square, obviously the remaining part can be covered using an L shape, right? This is exactly what I'm trying to do. So obviously the property holds. Then step 2, suppose when n equals to k, the property holds. It means what? 2 to the power of k times 2 to the power of k. So that's a big one. I don't know. I'm just trying to give you some. So there are 2 to the power of k, 2 to the power of k, right? And you randomly remove 1. I don't know. I just remove 1 in the middle. Okay? And suppose the remaining part can also be covered using a bunch of L shapes, right? So the $1 million question is, when n equals to k plus 1, what should I do? Right, all the way to here, we just basically follow the pattern. You don't have to think too much. But all the way come to here, I'm going to ask you some questions. Whenever I go to k plus 1, how can I make some magic and make it happen? Anyone wants to throw out some ideas? So Leo said, try to come up with an equation so we can plug in k plus 1. So Andy mentioned you can just double the side length, then just use the property from this. I think Andy actually has a very good direction. Maybe we can ask Andy to give us some ideas. How do you think? Why do you come up with such a conclusion?
Okay. So can you hear me?
Yeah, I hear you.
Yeah. Okay. So we know that when n equals k, when you remove one square, it works because that's our inductive hypothesis. We basically double the side lengths because that's what 2 to the k plus 1. So the area is quadrupled. So if one square is removed from that, the new one square is removed from that new large square, we find the quadrant that it's removed in, and we can say that that quadrant can be filled with the L shapes. And then as for the rest, I have to think about it. Yeah.
Okay, perfect. You already have a fantastic direction. You know, why am okay, perfect. Thank you. So why I think Andy's solution is better. I'm not saying Leo's solution is bad, because Leo's solution needs some equation that you can plug in and plug k plus 1. Just to be honest, it's kind of difficult to find out like an equation, right? This is not like something like the equation thing, because this is like a shape. What we're trying to, for sure, we are on the same page. We need to find out the relationship between n equals to k and n equals to k plus 1. They need to talk to each other. If they don't talk to each other, that's totally nothing, right? They need to talk to each other. So what is the very intuitive feeling? N equals to k and n equals to k plus 1. I think from the graphics perspective, Andy's solution is very understandable. Let's say when n equals to k plus 1, k plus 1, because we're looking at 2k plus 1 times 2 to the power of k plus 1, right? I need to find out, because the $1 million question is, I need to use my hypothesis and then come to here, do my work. So at the end of the day, I need to find out the relationship between my hypothesis and my current case. Andy actually gave us a very good direction. They just basically doubled the size. So how does this 2k plus 1 works like? I'm just going to give you here. Maybe I'll cut it into 4 parts. So I'm just going to do something fairly quick. Right? And for each part, you will have such a 2k, right? 2k, not 2k, 2 to the power of k, right? I'm just trying to give you guys a better understanding. 2 to the power of k, 2 to the power of k, 2 to the power of k. Okay. And Andy said, this is actually my original thought is like the 1/4, right? Whenever n equals to k, this is like basically 1/4 of my entire thing. So because I'm going to poke out, like I'm just going to remove 1 square from this entire thing. The 1 square, for sure, it will force into 1, 2, 3, 4, 1 of this 4, 2 to the power of k times 2 to the power of k case. Without the loss of generality, without the loss of generality, I'm just going to say I remove a square from here. Okay, according to our hypothesis, these guy, for sure, will be fully covered using the L shape without any overlaps, blah, blah, blah. Okay, the $1 million question will be the next. How can I take care of the other 3 parts? How can I take care of the other 3 parts? Think about it. Every single math competition problem, the numbers, they shouldn't be given for fun. There must be a very, very important reasoning behind it, right? For now, for this problem, it doesn't really give a number. It gives you a shape.
Wait, the rest would be 2k squared times 3, which has 3 as the factor.
Say that again. I'm sorry. So I didn't hear it so well.
So if we just ignore that quadrant, the other 3 quadrants will just be 2 to the power of k times 2 to the power of k times 3, which has 3 as a factor. So that means it's divisible by 3.
Yeah, but you're still gonna go for, yeah, but But Leo, you are still in the mathematical way, like the algebra way. So let's try to ground it a little bit. Instead of doing something too complicated, try to do something easier. Can we do some kind of like a geometry way to figure it out? For this problem, let's just try to do the pure geometry way. We try to use the hypothesis we did. Looks like we use it once. But think about, we still have 3 remaining 2 to the power of k times 2 to the power of k blocks. And I have such an L shape. Like I said, every single number is giving you for a reason. Every single shape is giving you for a reason. Nothing is actually giving you for free or for fun. Actually, I think Chris and Leo, like another Leo, already have the correct answer. What I'm going to do is, I'm just going to come to here, manually remove 3 blocks to here. See? The 3 blocks in the pretty much like the adjacent part, right? From like the adjacent part of the 4 different like grids, right? For each one, I'm just going to remove 1 block. So these 3 blocks will create a L shape. Is that right? And also, for each of this individual block here, I am actually removing a square from it. According to my hypothesis, these guys will be fully covered using L shape. These guys will be fully covered using L shape. And this guy will be also fully covered using L shape. Is that right? Plus, what I did, I just poke out an L shape. So this part can be covered by using an L shape. So that being said, my entire thing will be covered by using L shape. Is that right? You guys follow me?
But what if the squares that are cut out aren't on? Because it has to be a square, like a square that's cut out from any of the squares. It doesn't have to be on the corners, but it fits in the middle.
Exactly. That's a very good question. Because there's only 1 square removed. Is it right? The 1 square removed, no matter what, you will remove your first square in one of this 1, 2, 3, 4 quadrant. There's no way you remove square in the middle which covers 4 quadrants, right? There must be falls into one of them. You can fall to here. You can move here. I don't really care. As long as you remove into 1 quadrant, this quadrant, according to my hypothesis, it will be fully covered by using the L shape. You always leave the other 3 quadrant fully untouched. I'm going to be using exactly the same strategy to manually poke 3 from the intersection parts and do my magic one more time.
Oh, right. Yeah, I don't know what I was thinking.
No worries. Yeah, it's always good to ask me questions, right? It's always good to ask me questions. So I think that's actually the solution for this problem. You're probably going to write a lot of English rather than put like a big number or like formula or something. But I think this is actually something you can just have a feeling how it works. So far, so good? Okay, if all good, let's go for a 5 minutes quick break. And then we're going to resume after the quick break. All right, 5 minutes. I'll meet you guys around 8:13. All right. If you have any questions in this break, let me know, and I'm here to help you guys. Okay, let's go for a quick break. Grab some water. Okay, guys, so let's continue. Okay. So let's continue. So now we're going to see another problem. So this problem is a little bit difficult. Let's try to do a little bit difficult problem, how to use the mathematical induction method to solve the real problem. So this is our question number, I don't know, that's number 4, right? Let real numbers a1, a2, all the way to an, such that a1 plus a2 all the way to an, they equal to 0. The total sum of all those numbers equal to 0. And a1 absolute, a2 absolute, all the way to an absolute, less than 1. N is a positive integer, n is greater than 2. Let Bn equals to an over n. N is also this positive integer. Please prove B1, B2, Bn absolute less or equal to 1 over 2 minus 1 over 2n. N is equal to this. Of course, n is greater than 2. Okay. So this problem is also a very typical mathematical induction method. You won't be able to do. I think you might also be using the arithmetic sequence, geometric sequence related thing, but mathematical induction method is going to help you significantly in the process. So again, we have a bunch of numbers, a1 all the way to an. Their sum is equal to 0. Their absolute value sum is lesser than 1. And I define another Bn. Bn is actually an over n. With all those information, try to prove Bn is lesser than such a weird expression. Trust me, as long as you see a weird expression, always try to use the mathematical induction method. Because using like a basic method is kind of difficult for you to squeeze out such a weird expression. Well, the good part of mathematical induction is you can just suppose this is valid, right? You only need to do another proof based on your hypothesis, go to n plus 1 or k plus 1. So you're kind of like, or should I say, this proof process can be a little bit straightforward. If you guys follow me, right? This is the why sometimes you want to choose the mathematical induction method. So let's get started. So mathematical induction, 2 steps. Let's do this. I'm just bluntly doing this, right? Step 1, let me change the color. Step 1, n equals to 2. N equals to 2, it means what? A1 plus A2 equals to 0. So of course, A1 is minus A2, right? The condition give you this. A1 absolute value, A1 absolute, A2 absolute, lesser than 1. Because A1 and A2, they are basically the same thing, talking about the absolute value. So that being said, A1's absolute will be lesser than 1 over 2. Okay? The question asks what? Prove this. B1 plus B2. So B1 plus B2 absolute value will be equal to A1 plus B2 will be A2 over 2, right? Will be A2 over 2. So because A2 is minus A1, so this guy will be A1 over 2, right? I just jumped one step because A1 and A2, they have such a relationship. So that one is lesser than 1 over 4. 1 over 4 is actually 1 over 2 minus 2 times 2. So the property also holds for the first. I think the base scenario pretty easy. Should have no problem. Step number 2. when, or we'll say suppose, right? Suppose when n equals to k, this property holds. That being said means what? A1 plus A2 all the way to AK equals to 0. A1 absolute, A2 absolute, AK absolute less than 1, right? Within these two conditions, I can figure out B1 plus B2 all the way BK less than 1 over 2, 1 over 2K, right? This is I close my eyes. I blindly doing this without any pressure. Okay? Now, the $1 million question part is, now we need to examine n equals to k plus 1, right? Whenever n equals to k plus 1, let's have a look at this condition. What this condition looks like. That's going to be A1 plus A2, AK plus A plus 1 equals to 0. Is that right? Okay. What else? Think about it. What we did for the first problem. We find A1 plus A2 equals to 0. And then taking from there, I do some magic. I find out, okay, A1 and A2, they're actually just basically the same thing, but with equals, always like a sign is different. For now, all my focus on what? AK plus 1, right? This is all my focus. I can do exactly the same thing. A1 plus A2 all the way to AK is minus AK plus 1. Is it right? So I still have another condition I need to do. A1 absolute, A2 absolute, all the way AK absolute, AK plus 1 absolute, lesser than 1, right? This is what I have. These two conditions, they come all together as a bulk, right? So let's have a look how this one looks like. Because I know A1 plus A2 all the way to AK, absolute value, plus AK plus 1 absolute value. This guy will be lesser or equal to A1, A2, AK, AK plus 1, right? This guy will be lesser than 1 because this is actually given by the condition. Is that right? So don't forget, this part and this part, they have the same value. It's only different for the absolute. So it means this part is also equal to AK plus 1, absolute. Is that right? So therefore, AK plus 1 absolute will be lesser than 1 over 2. Why I'm doing this? Don't get lost. I'm doing this because this is exactly the same thing. Previously, I did some magic. I find A1 absolute lesser than 1 over 2. Now, I must do the same thing to find out AK plus 1 absolute lesser than 1 over 2. So that being said, okay, everything is harmonic. Nothing becomes a little bit buggy. Okay? So now, let's have a look how our left-hand side looks like. The things I need to prove is this. Whenever it goes to BK plus 1. Is that right? Okay. B1, B2, BK. I just put BK plus 1. Absolute value will be lesser than, because I want to use my hypothesis, right? My hypothesis is here. Oops. My hypothesis is here, right? I want to use my hypothesis directly into my K plus 1. This is very intuitive. Is that right? Every single step is very intuitive. I want to use this. So that one will be BK, B1, B2, all the way to BK plus BK plus 1, right? So this guy, according to my hypothesis, will be 1 over 2 minus 1 over 2K, right? This guy, don't forget, BK plus 1 equals to what? AK plus 1 over K plus 1, right? What is AK plus 1? Less or equal to 1 over 2. Is that right? Very intuitive. Every single step. You're not. Well, if I add them together, I got a problem. I get this guy will lesser than 1 over 2, 1 over 2k, 1 over 2k plus 1. Let me go back to the original hypothesis. If everything works fine, I'm supposed to have what? 1 over 2 minus 2k plus 1. Is that right? I am supposed to get 1 over 2 minus 2k plus 1. What I got is not what I need. Is it right? Okay, all the way to here, you have any questions? Give me some feedback. Score up. Any questions so far?
So there's absolute value plus absolute value of bk plus 1. Can it also be like minus absolute value of bk plus 1?
It doesn't matter. Yeah, of course you can put minus, but you put minus, it doesn't change your dilemma. You're still gonna end up with a 2k here. Is it right? There's no way for you to get up this 2k. 2k, you can be plus, can be plus, can be minus, can whatever you like, but you always have 2k here. Well, you need to do is actually 2k plus 1. This one doesn't make sense. You don't really talk to each other. Is it correct? You guys follow me? Yes or no? So what I'm trying to say is, if I all the way for now, I basically use my common sense. I do whatever I have to do. I'm crossing my fingers to get, this 1 over 2 minus 1 over 2k plus 1. But unfortunately, life is not so good. I can't get 2k plus 1. So this is actually a very commonly seen situation in the mathematical induction method. It means that your direct approach doesn't really work properly. You need to somehow do some magic to make it happen. You need to do some magic to make it happen. Because if you directly do this, you only end up with this. So how can I do the magic to make it happen? We need to think about it. For now, I have this stupid 1 over 2k. I don't really like this 1 over 2k. If do some magic, I can get rid of this 1 over 2k. My life can be pretty fantastic, right? So I need to do some magic to get rid of this 1 over 2k in order to make my life easy. But can I just put 1 over 2k and then minus 1 over 2k? It doesn't make sense. You need to use the thing you have already got and then do some construction. Do some construction to have what you need. Let's have a look. You are talking about this 1 over 2k thing. Where you can get 1 over 2k? Look at here. You just figure out ak plus 1 absolute value is lesser than 1 over 2. And you kind of know that bk plus 1 is what? ak plus 1 over k plus 1, right? So my question for you guys, who can tell me how can I construct out this 1 over 2k thing? By observing this and this, who can tell me how can I construct out this 2k 1 over 2k thing? You guys follow me here? This is very important. Okay, every single answer is not because I have the right answer. I'm reading. Okay, let's do this according to the official solution. No, we need to think about it. Now our $1 million question is to figure out this 2k, 1 over 2k, right? As long as I got a 1 over 2k, I can somehow get canceled with this and do some magic afterwards. But how can I find out this 1 over 2k? I cannot just do it from nowhere. I must use the condition I already know to construct out this 1 over 2k. This part I already know. AK plus 1 is lesser than 1 over 2. Okay. And I know that BK plus 1, all those kind of weird BK things are based on this AK over K, AK plus 1 over K plus 1. And what I need is 1 over 2K. Very intuitive. I don't know if this seems intuitive to now. Very intuitive. You want to create a AK plus 1 over K. As long as you have AK plus 1 over K, you are kind of having a 1 over 2K. Is it correct? You guys follow me? I'm actually teaching you what is the rationale behind it. You have any questions? So far, so good? Because I have, okay, my $1 million question is I need to figure out a 1 over 2K, right? Because 1 over 2K is actually subtraction here. I need to figure out something and just get rid of it. But how can I create this 1 over 2K? I have a AK plus 1 is less than 1 over 2. And I have like kind of BK plus 1 is AK plus 1 over K plus 1. Somehow, if I create an AK plus 1 over K, this is going to happen. I'm going to have like a 1 over 2K. Somehow figure out my need. And David asked me, how are you going to do this? Trust me, I will show you in a bit. This is the beauty, or this is the crazy of the construction method. Okay, if all good, this is the $1 million question for this part. We guys are learning the mathematical thought behind it, not only one problem or two. Okay, so that being said, when n is equal to k plus 1, the left-hand side becomes b1, b2, all the way bk plus 1, right? Okay, and you told me bk plus 1, that's not a big deal. AK plus 1, K plus 1, right? How can I have my AK plus 1 over K? Construction. Construction is just, I'm going to add AK plus 1, and then I'm going to minus AK plus 1 over K. Add a term, subtract a term. This is very common for the construction method, right? All the conditions holds the same. Okay. I'm going to do a little bit quick analysis. B1 plus B2, BK minus 1. I'm going to, because I already have a K here, right? I'm going to make this also as AK over K, right? I think this is quite understandable. I'm not doing any magic. So this is going to be what? AK plus 1, K plus, I think this is going to be you guys follow me here? No magic. I just basically do some rearrangement. That's it. No magic. I just basically do some rearrangement. Why I change this? Because I see AK plus 1 over K, right? So I just basically give a K out. So therefore, everything can be here. This is not the magic. All right. So according to what I need, what I have before, B1, this guy will be lesser or equal to B1, B2, BK minus 1, K, AK plus 1, and K plus 1 minus K, AK plus 1, right? This is not a magic. I just break them into two absolute values. You guys should be very familiar with the absolute value inequality. Okay, so far so good? Okay, but still, this guy looks a little bit different with my original hypothesis, right? What does my original hypothesis? My original hypothesis, who can remember? What is my original hypothesis? my original hypothesis says this. When when n equals to k, I have a1 plus a2 all the way to ak, right? A1 absolute value, a2 absolute value, all the way ak absolute value lesser than 1, right? So far so good? And it's not exactly the same as what I have here, right? So as I said, as long as this work, I'm going to say b1 plus b2 all the way plus bk. This guy will lesser than, what is that? What is the hypothesis? So 1 over k. Yeah, 1 over 2 minus 1 over 2k, right? But they're not exactly the same. Wow, this is the magic part for this problem. Okay, check it out from here. For this problem, my original hypothesis says this. I totally agree. No objections. Everyone is perfect. However, I say AK. AK. You think AK is like a number, right? 1, 2, 3, 4, 5, whatever, whatever. But think about it. AK can be anything, right? AK just like a denotation. Is that right? AK does not have to be really 1, 2, 3, 4, 5. AK can be whatever, like a denotation. So instead of putting the AK, I can just let AK as a house, as like a room. You can put everything in. You can put 1 in. You can put 2 in. You can put whatever in. And also, you can put AK plus 1 in. AK plus 1 in. Is that right? AK just like denotation. AK can be whatever. So I don't really care what AK is. I can put whatever AK it is. You guys follow me? So what about I put AK just as, I don't know, AK plus 1. I'm going to give it a big name, maybe big AK. I'm just going to give it like a different name. You guys follow me? So that being said, as long as I can have A1 plus A2 all the way to AK minus 1, and then I have such a big AK, I can always make sure this guy holds. Is that right? But here, bear in mind, this is no longer going to be an easy BK. This is going to be AK over K. Is that right? So this is the tricky part for this question. It used to be a single variable AK. Now I'm going to change it into a big room. This room, you can put whatever guys there. You can put an AK. AK can be like a attendant. They can be a single guy. They can be a couple, right? You always give the same price to like, you have a condo, you rent for 200 bucks, like 2,000 bucks. You come in one guy, you charge 200, like 2,000. You come in with a couple, you still charge 2,000. Nothing changed. Okay, that's the $1 million part. If you can agree with me in this part, check it out here. This part will be my magic AK. And this part will be my magic BK. Is it right? You guys follow me in here? So that being said, even though this expression looks pretty nasty, B1, B2 all the way to BK minus 1, and then this is a little bit of a weird thing, but I don't care. This also be considered as BK. Is it right? You can still use exactly the hypothesis you did for the last n equals to k scenario. I can claim this guy will be lesser or equal to 1 over k minus 2k. Are you guys following me here? I need some response. This is a very techy part. Do you guys follow me? If AK just a denotation, then what is the value of original AK? I don't really care. AK just like a denotation. I do whatever AK it is. Today AK can be 1. Tomorrow AK can be like a polynomial. Like the third AK can be a trigonometry. I don't really care. But it 100% falls into such a pattern. A1 plus A2 all the way to AK equals to 0. A1 absolute all the way to AK absolute equals to 1. This is exactly what I'm looking for. So this is a very deep mathematical thought. You're not close your eyes, blindly use, okay, it is what it is. So that part gives you 1 over 2, 1 over 2k. Okay? And this part, as long as you come to here, you're almost 100%. You're 99% done. This part, because AK plus 1 absolute is less than 1 over 2, so this is k plus 1 minus k 1 over 2. You just close your eyes, blindly put it in. This guy will be 1 over 2 minus 2 k plus 1. You guys follow me? This part will be easy. You just close your eyes. You just basically do this. That's it. Or the $1 million question is this part. What are you going to do for this part? Okay, let's have a very quick recap. I want you guys to understand the beauty of this problem. Okay. I think at the very beginning, nothing really magic. You just basically let n equals to 2, do some magic, whatever. And then whenever n equals to k, it holds. If you close your eyes, blindly do this, all the way you come to here. 1 over 2 minus 1 over 2k and this. But you don't need this, 1 over 2k. So intuitively, we need to do some construction to get rid of this 1 over 2k. But you can't only put a 1 over 2k here because there's nothing to do with anything. So intuitively, you want to screw up, find out what is the rationale behind this problem. You find out this problem has AK plus 1 lesser or equal to 1 over 2. You find out BK plus 1 equals to AK plus 1 over K plus 1. Intuitively, if you want to figure out this 1 over 2K, you'd better use something AK plus 1 over K, rather than just put a 1 over 2K there. As long as you know this part, you'll basically follow the trend all the way come to here. This is another $1 million part. You need to understand AK plus 1. This is like just a denotation. You put whatever you like. It can be a house, a couple, like a single guy, whatever. As long as this one works, you'll be able to use this mathematic. You're going to be able to use your hypothesis one more time to figure out this problem. Trust me, this is a very good problem. It reflects a very deep mathematical thinking. This is only a denotation, nothing more than a denotation. So far, so good? Okay, if all good, let's go for an AMC problem, right? Don't forget, we're basically jumping from AMC and like a Canadian. So we're gonna give you a problem 2007 AMC 12A, question number 25. So this problem is not so difficult. It's actually an easy problem. Okay, so this is like a Chinese problem. So what content this problem? It's like, but I think it's a very good problem because if you go to like the COMC or like the Euclid, last problem in Euclid, this is like the same complexity level. So let's have a look at a AMC problem. A set of integers, spacey, if it contains no more than 1 out of any 3 consecutive integers. How many subsets? 1, 2, 3, all the way to 12, including the empty sets are spacey. This is the last problem from AMC, right? But if you see, like, this is not a very complicated problem. If you understand like the rationale of this, what is called the induction. So the question says what? So a set of integer is called spacey if it contains no more than one out of any three consecutive integers. Okay, you guys understand the English. So how many subset of 1, 2, all the way to 12, including empty set, are considered to be spacey? You know what? AMC doesn't really ask you to do any proof, right? As long as you guess out the number, it's good to go, right? So for the AMC problem, we don't really have to do a very rigorous proof. As long as you find out the relationship, it's good to go. Any of this kind of problems, my suggestion is always start with some numbers. If you totally start sitting there rolling your fingers, I don't think you can get an answer. Get your hands dirty, list out some numbers, you maybe get an idea how this guy looks like. Let's have a quick look. What about S? They ask you to do S12. S12 is too much. Let's get started maybe from S0. Because the question says empty set is also considered to be spacey. So, right, this is like the empty, this is like nothing, right? Means nothing. So this is also good. So S0 really has like 1 as spacey, right? Then what about S1? S1 just means there's only 1. There's only 1, so 1 is nothing, 1 is 1. So you have 2, right? 2 subsets are considered to be spacey. You just try to write 2, 3 to 4 to get an idea how it looks like. Then what about S2? S2 means you have 2 things. Because you can't have any one out of no more than 1 out of any 3 consecutive integers. So you can have 1, can have 2, can have nothing. But you can't have 1 and 2 altogether, right? This will be more than 1 out of consecutive 3. Have 3. That's 3. 1, 2, 3. 1, 2, 3. Then you have 4, right? Is that right? You can't have 1, 2, 3 because there are 3 consecutive. S4. 2, 3, 4. 1, 2, 3, 4, and 1, 4. 1, 4 is okay because they're not 1 out of any consecutive 3 because they're jumping more than 3. So, and also nothing, you have 6. All the way come to here. Think about it. Because AMC, like I said, most of this AMC problem should be very intuitive. They shouldn't be having a crazy number for you to denote. Think about it. What are you going to do from here? S0 equals to 1. Okay. S1 equals to 2. 2 equals to 3. 3 equals to 4. 4 equals to 6. Oh, sorry. 4 equals to 6. Trust me, all those kind of things must be kind of like a relationship between some numbers, so on and so forth. Must be some relationship between some numbers, so on and so forth. Actually, this is actually given by the AMC. If you do not really want to do the rigorous proof, you can actually guess out Sn equals to Sn minus 1. So that's Sn minus 3. 6 equals to 4 plus 2. 4 equals to 3 plus 1. So Sn is equal to Sn minus 1 plus Sn minus 3. This is also considered to be induction, right? Because the induction is pretty much what's the relationship between u and n. So in our induction, we see n minus 2k, n minus 2k plus 1. This is also induction. This is like a n minus 2k, n minus k minus 1 and n minus k minus 3. Is that right? If you want to, I know this is very difficult, but this is more like a shortcut solution given by AMC. As long as you figure out such a relationship, you will be able to, S12. You just basically have to list out what is S0, S1, S2, all the way to S12. 1, 2, 3. Then you will be able to calculate 4 or 5 all the way to 12. This one, there's no trick, 129. There's no trick. You just basically calculate out one by one, and you get 129. But I'd like to give you a little bit of analysis. Why you have this? What if you have no idea Sn equals to Sn minus 1 equals to Sn minus 3? You can still do a little bit of analysis. What is the analysis? Think about it. If I want to find out 1, 2, all the way to, let's say, n plus 1, right? I'm looking about Sn plus 1, okay? I want to find out the spacey subsets of this Sn plus 1. What should I do? I just basically break my condition, my problem into two scenarios. One scenario is, in my final answer, there is no n plus 1's term. There's no n plus 1's term in my collection. Or there is n plus 1's term in my final answer, right? You only have this two possibilities, no other scenarios, right? You just either have n plus 1 or you not have n plus 1. If you do not have n plus 1's term, that being said means what? The total number of the spacey subset of n plus, of this Sn plus 1 total will be exactly the same as 1 all the way to n. Is that right? So that is actually Sn. Is that right? If I do not have my n plus 1 term, so the total spacey subset will be exactly the same as I just close my eyes and cross out n plus 1, directly have the first n terms. That's going to be Sn. Is that right? You guys follow me? While the other scenario is I do have the n plus 1 term. 1, 2, n minus 1, n minus 2. Let me see. N minus 2, n minus 1, n plus 1. If, for God's sake, I basically choose n plus 1, then unfortunately, I cannot take n. I cannot take n minus 1 for sure, right? Because they're considered to be more than one of the consecutive three numbers, blah, blah, blah. So that being said, as long as I have n plus 1 term chosen, I can only choose all my magic from the first n minus 2 term. So that being said, in this scenario, the total subsets will be Sn minus 2. So my total scenario, just one of these two scenarios, nothing can be more. So Sn will be equals to Sn minus 2 plus Sn. You guys follow me? Yes or no? Please give me some feedback, please. Any questions? So this is also a more like a realistic way to basically figure out what is the relationship between this. And this is, for AMC, you don't really have to prove. For if this is a COMC, they're going to really ask you to prove why this is. You're going to put a lot of mathematical induction. But for AMC, as long as you can logically figure out what it is, you're good to go. Okay, same thing. You just do some calculation, figure out the right answer is 100. Did you mean Sn plus 1? Yeah, Sn equals to Sn minus 2 plus Sn. So that being said, Sn plus 1 will be equal to Sn. Sn plus 1. Yeah, excuse me. Sn plus 1, yes, will be equal to Sn minus 2 plus Sn. Yeah, I have a typo here. Sn plus 1, because this is n plus 1. Oops. Right? Sn plus 1 will be Sn minus 2 plus Sn. Okay. Actually, this is a very important induction, right? This induction thought is also very important for the Canadian Euclid exam. Think about it. I think most of you guys actually been to my Euclid bootcamp. Do you still remember this problem? We have no time to say this problem today, but do you still remember this problem? It's a little bit laggy. Do you remember this famous add-in sequence problem? We talk about it in our Euclid bootcamp, right? This is a crazy problem. I don't want to, yeah, this is a crazy problem, right? So this is actually what? This is a problem from, still remember? A problem from 2012. 2012, Euclid, problem number 10. Do you still remember we use exactly the same strategy? Find out, do I have the last term? If I have the last term, what about the odd one? What about the even one? Blah, blah, blah. We use more than 30 minutes talking about this one problem, right? Okay, I'm going to give you another problem. So we won't say that today as well, but I just want to say why this is very important for Euclid. Problem number 2. If you check this problem, this is a problem also from Euclid, and the problem is 2009. Euclid, question number 10. This is exactly the same strategy. So what I'm trying to say, if you want to do a good job for Euclid question number 10, mathematical induction is extremely important. This is in induction, right? You find out the relationship between your previous term, previous 2 terms, so on and so forth. Okay? So far, so good? So trust me, this is very important for Euclid as well. Like, you might not see this so often because most of the students, they don't really have time to do question number 10. And also the same thing applies for the number theory. These are actually very important. As a wrap up of today's lecture, let's have a look at another problem. The other problem is a problem like this. Question number 5 or number 6, I can't remember. So this is another problem. We have a sequence AN can be defined as follows. A1 equals to 1. AN equals to AN minus 1. AN divided by 2 Gauss function. You see a problem like this, it won't be easy problem, right? Because the Gauss function goes to there. N can be 2, 3, whatever. Proof. There are infinitely many terms in AN which can be divisible by 7. Okay, first of all, you guys should be familiar with the number theory. Is that right? Can you guys give me like a little bit of idea? Especially for the new guys, you're familiar with the number theory, modular arithmetic, at least number theory, modular arithmetic. Is that right? Yes or no? When I have them, because the old students, they should have no problem. I'm 100% sure. But for the new students, because we already covered that, we already covered the number theory parts in our last year, 2019. Okay, a problem like this. A1 equals to 1. AN equals to like a kind of recurrence formula, right? There are infinitely many I told you before, right? As long as you see something asks you to prove there are infinitely many, most likely you're going to use what? Construction method. Is that right? You need to construct out some infinitely many things, and taking from there, you'll be able to figure out what it is. Is that right? Okay. So, a problem like this, how can we get started? Like I keep saying, whenever you see a weird problem, don't be panicked. Try to list out some terms first as a start. At least you know what you're talking about, right? So let's try to list out some terms. A1 equals to 1. A2, 2. A3, 3. A4, 5. A5, 7. Ah, I already find one guy which is divisible by 7. Is that right? Okay. So my ultimate goal is trying to find out there should be some other numbers more than 5, but they can also let that number divisible by 7. Is that right? So basically what I'm trying to say, I find A5 equals to 7. My first case is done. Step number 1, right? We're still in the mathematical induction. Don't forget, we're still in the mathematical induction. So step number 2, what I'm trying to do, okay, let I have n greater than 5. 7 is the divisor of an, right? Let I find, so this is same thing, let n equals to k. And with all those conditions, I need to find a m greater than n. Also 7 is a divisor of am. You guys follow me? Yes or no? Yes or no? This is what we're looking at, right? We're trying to find another m which must be greater than n, right? So I'll be able, because for now, m and n, they're not consecutive for sure. I need to find a greater m. As long as I find a greater m, I can find another greater m prime. So they are jumping one after another. So every single problem we give you something different. It's not always the base case, but in your homework, it's a lot more easier. You can use the basic one. Okay. So here we need to do some magic. Let's have some look. Construction is always either start with a magic or end with a fairy tale, right? You can't just like blindly doing blah, 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 blah. This is not how construction works. If you guys go to my advanced mathematical thought lecture, you're going to find out this, right? Magic, there should be some magic in the construction method, either in the very beginning as a fairy tale, and we always go for it. Construction method is always, we start with once upon time, and then we end with, and then live happily thereafter. And we leave all the middle part with the magics, fairy tales, or black magics, so on and so forth. But beginning and end, they're always beautiful. So that's how construction works. So let's try to do something like this. Oops. According to what I write here, 7 is the divisor of an. So an is congruent to 0 modulo 7, right? Let's try, like I said, as long as we learn the modular arithmetic, forget about the stupid 7k plus 1 thing. Let's jump to the more high-techy way, modular arithmetic. An is congruent to 0 modulo 7. A2n. A2n is what? Using this magic. A2n can be written as A2n minus 1 plus an, right? Because an is congruent to 7. This guy will be congruent to A2n minus 1 modulo 7. Is that right? Any objections? Because an is divisible by 7. So like the remainder will be A2n minus 1, right? This will be the same remainder as A2n minus 1. Okay, let's continue. A2n plus 1 equals to A2n plus an equals to A2n modulo 7, right? Same thing. AN will be congruent to 7, will be the divisible by 7, so the remainder goes to A21. A21 congruent to A21 minus 1, A21 plus 1 congruent to A21. So that means that this is very interesting. A21 minus 1 congruent to A21 congruent to A21 plus 1 modulo 7. Is that right? So far so good? Okay. Here, let me just try, because they keep saying this is congruent to A21 plus 1 modulo 7. Let's try to let A21 minus 1 is congruent to R modulo 7. Okay? This is not magic. I just try to, you keep telling me everyone is congruent to A21 minus 1 modulo 7. Let's just put an R there, okay? There's nothing magic. If R is equal to 0, okay, if A21 minus 1 is congruent, it's actually divisible by 7. I just let M equals to 2N minus 1. I'll always make sure 7 is congruent to AM. Is that right? My work is done. If I can get A21 per se, A21 minus 1 per se, it's just divisible by 7. My work is done. No need for me to do anything. Is that right? Yes or no? I hope you guys still follow me. If you get lost, please let me know, okay? Everyone, not only 1 or 2 guys, everyone. Okay. But life is not so beautiful, right? We need to figure out if R is not equal to 0. If R is not equal to 0, I have to do a crazy construction. Let me examine the following 7 numbers. Let me try to find out the remainder for these 7 numbers. This is the construction. I'm sorry, this is the construction. It's kind of the construction like, you know, those guys, you know, like we create a Russian problem using different squares. We put them together. Right? This kind of, and then we use how to use like the lattice points to figure out a problem. This is the construction. Let's try to figure out how this 7 numbers looks like. Let's start from the second one. 4n minus 2. According to our definition, 4n minus 3, 2n minus 1. Is that right? This guy will be congruent to A 4n minus 3 plus R modulo 7, because A2n minus 2 is actually R modulo 7. Right? Okay. A 4n minus 1 will be equal to what? 4n minus 2. 2n minus 1. This is not a magic. You just basically use the definition. An equals to blah, blah, blah. An floor function, blah, blah, blah. Okay. I just know this guy is congruent to what? A 4n minus 3 plus R modulo 7, right? Well, this part is congruent to R modulo 7. Altogether, this guy will congruent to A 4n minus 3 plus 2R modulo 7. Is it right? You guys follow me? Okay, let's continue. What about 4n? Right, according to the definition, it goes to this. 4n minus 1 congruent to A n minus 4n plus 3 to R modulo 7, right? This is what we just did. This guy equals to what? 2n? Don't forget, 2n is congruent to 2n minus 1. They're all R modulo 7, right? what I'm trying to do here. 4n minus 3 plus 3r modulo 7. Is that right? Oops. Sometimes it's like too hot. It goes like this. Okay, you know what? I can skip all the other work. Order a 4n plus 3 can be congruent to a 4n minus 3 plus 6r modulo 7. Okay, oh my God, it means like this. A 4n plus 3, 4n plus 2, 4n plus 3. These guys are actually written as what? 4n minus 3, I don't care. 4n minus 3 plus r modulo 7. The next one is what? 4n plus 3 plus 2r modulo 7. All the way 4n plus 3 plus 6r modulo 7. Okay, here I'm going to use a little bit of high-techy thing. Does anyone know what does this thing mean? You have like, you can put it like an A, it doesn't matter. A plus r modulo 7, a plus 2r modulo 7, all the way a plus 6r modulo 7. Do you know how this kind of 7 guys mean? Do you know this guy has a name? We didn't mention this in our lecture, unfortunately. But I think but I don't know for the other guys. Have you happened to know this? Yes or no? So you are actually having a set, right? You have 7 numbers. These numbers are actually, the first one is A. The second one is A plus R modulo 7. The third one is A plus 2R modulo 7. And all the way to 6R modulo 7. This is actually have a name. This is you don't have to know this. I just want to give you this expand their horizon. This is a complete system of 7 residues. A complete system of 7 modulos, because you have a 7 here. According to the number theory conclusion, these 7 numbers must be one of them can be divisible by 7. Yeah, if you don't know this, it doesn't matter. If you don't know this, it doesn't matter. This is not a big deal. But this is like this is what we call the complete system of 7 residue. I'll give you an example. If I give you 3 numbers, a plus 1 modulo 3, a plus 2 modulo 3. These 3 numbers, what we call is complete system of 3 residues. I must have one number, at least one number can be divisible by 3. Have a plus 1 modulo 4, a plus 2 modulo 4, a plus 3 modulo 4. We call this is a complete system of 4 residues, which must have one value, at least one guy, divisible by 4. All the way, if have 7, it doesn't matter 1 or 2 or 3. You can just basically, as long as you jump, can be r, 2r, 3r. For my case, I'll put r equals to 1 to make our life easier, but same thing, no difference. So this guy will be called a 7th complete system of residues. You must have one guy divisible by 7. It doesn't matter if you don't know this. This is a number theory lecture problem, not our focus. Our focus is mathematical induction. We actually prove that as long as you here, follow me, in the step 2, I find out a number n greater than 5 can be divisible by 7, I must therefore construct another number greater than 5, but also divisible by 7. So this guy says everyone here will be divisible by 7. Oops, I Just okay. I can find out at least one of these guys will be divisible by 7. This is not a big deal if you don't understand what I'm talking about. This is not a number theory lecture. Just want to give you guys a little bit expansion for this. So this, I think all the problems I gave you are actually in the Euclid number 10 complicity. Like in today's lecture, Euclid number 10 or number 9 B, C part, or COMC C part from the second problem. So this aligns with our Hawk lecture. The other lecture can be a lot more easier. We just go for AMC10. It's good enough. And I think that's pretty much what I want to say for today's lecture. You have any questions for me? Try to understand the big direction rather than struggling for the corners like details, right? That's a different way to think whenever we go to a high-level math competition. This lecture might be a little bit difficult for some of the guys if you're not so familiar with mathematical induction method, but trust me, this is pretty much very important for the last 2 problems in Euclid and COMC and AMC as well. Okay, so I have a question about homework for a tough one. Can I just? Oh, yeah, you can talk to me later. You can talk to me later. All right, so I think that's pretty much for today's lecture. Thank you, guys. And I'll upload assignment to our Google class. You have 1 week to finish the assignment. The assignment is a lot more easier than what we're trying to talk about here. So hopefully you can enjoy the assignment. All right, so that's pretty much. I'll see you guys next time. Bye, guys. Ciao, ciao.